Welcome to Global Virtual School. Students, this is your first year chemistry class. I am Dr. Ijaz Bano. Students, we are on chapter number 2, that is atomic structure, and the topic for today's is from the chapter 2 is 4 quantum numbers, the quantum numbers. Students, basically quantum number is actually used to describe the position of the electron, and after completing this quantum number, that are total 4, you will be able to distinguish among principal energy level, energy sublevels and atomic orbitals. Previously you already know about the principal energy level, that I used to call it shell or orbit, and also you will be able to describe the concept of orbitals, not orbit, concept of orbitals, and because you are already familiar with the orbit but not familiar with the orbitals, so this is very important topic. You must have focus what I am discussing today. Before going into detail, I must recall you about your previous knowledge from 9th or 10th. You will be quite familiar about the concept of S and P subshells. S of the spherical shape and P of dumbbell shape, and further P have 3 orbitals, that are Px, Py and Pz, due to their orientation in the space along x-axis, y-axis and z-axis. And in this topic we will even discuss more about the subshells and the orbitals to describe the position of the electron in an atom. Basically, the quantum number, this is was given by the Schrödinger in 1926. He gave an equation, and the solution of its equation gives the quantum numbers that describe the position of the electron. And according to that, electrons are treated as moving with wave-like motion, not in a state. Just according to this Schrödinger's wave equation, consider that electrons move in a wave and in the 3 dimension in the space, like x-axis along y and z-axis. It is not revolving on a single path, and while it's revolving in 3 dimension, its motion is like a wave. Its motion is not like a straight, its motion is like a wave, zigzag motion. And this concept is different from the Bohr's atomic model, and it also specifies the distance of the electron from the nucleus. In other words, you can say the size of the atom. And the solution of Schrödinger's wave equation gives certain mathematical integers, you can the numbers that we are going to discuss in this lecture, that are called the 4 quantum that are called the quantum numbers. So there are total 4 quantum numbers which can describe the electron completely. And remember this, out of these 4, the first 3, principal quantum number, azimuthal and magnetic quantum number, these were given by the Schrödinger, and while the last one, that is spin quantum number, represented by small s, that was given by Gauss-Schmidt. So 3 by Schrödinger's, and last one by Gauss-Schmidt. And these 4 basically completely 4 quantum numbers describe the position of the electron. And here come to the first quantum number, that is principal quantum number. It is represented by small n, and basically principal quantum number describe the size of the orbit. If you remember, previously I used the word orbit, shells or energy level in Bohr's atomic model. These are the for same, if it is orbit, it is shell, or it is the energy level. That shows the position of the electron, either it's in the first shell or first orbit or first energy level, or the electron is in the second shell or second orbit or second energy level. And the distance of the electron from the nucleus, that shows the size of the atom. So principal quantum number determine the size of the orbit or shell or energy level and the distance from the nucleus. Greater the distance from the nucleus, larger will be the size of the orbit, of course. And it starts with the positive number, that is 1, 2, 3, 4 and so on up to infinity. So this has a non-zero, its value is not a non-zero, its value is always start with 1. This table will explain you more about the principal quantum number. If principal quantum number n, it has value 1, then we call it the K shell, and capital K, remember it's the capital K shell, K energy level, or you can say K orbit. N is 1 and it is K shell. When n is 2, it is L shell. When n is 3, it is M shell. When it is 4, it is N shell. K, L, M, N, these are capital letters for representation of the shell number, or you can say the orbit number. And you can calculate the number of electrons in these orbits by using formula 2n square. Let I calculate for you. This is the formula 2n square, and when n is 1, 2 into 1 square. 1 square is 1, and when this 1 is multiplied by 2, then answer is 2. So first orbit or first shell, it contains maximum 2 electrons. And for the second, when n value is 2, 2 square, it's the 4. 4 multiplied by 2, then you got 8. So maximum number of electron in second shell or in second orbit is 8. Remember this. I am going to use this in the next slides or in the next quantum numbers. When n is 3, 3 square is 9, 9 multiplied by 2, then it is 18. So the third shell or third orbit has maximum number of electrons that are 18. Similarly, when n is 4, then 4 square is 16, 16 multiplied by 2, then it gives you 32. So the maximum number of electron in fourth shell or n shell, that is 32. So I am going to recall these, remember these for the upcoming slides. Overall, briefly I tell you, principal quantum number represented by small n. Its values start from 1. And it shows basically describe the size of the orbit, and they are represented by K, L, M, N, and the maximum number of electrons are calculated by using formula 2n square. So the higher the value of n, greater the size of the or you can say the distance of the electron from the nucleus. And the second is azimuthal quantum number. This is represented by small l. Azimuthal quantum number is represented by small l, and this is also called the sub energy level or sub energy shell or subshells, and it describes the shape of an orbital. Its value is always 1 less than that of n. This is important. Its value of L is always 1 less than principal quantum number. If principal quantum number is suppose n, then L value will be n minus 1. So L is always equals to n minus 1. So minimum, if minimum value of n is 1, 1 minus 1, it means 0. So its value start with 0 and maximum is n minus 1. So again I am repeating that its values value of azimuthal quantum number L is always equals to 1 less than n, 1 less than principal quantum number. So its value start with 0 and the 0, 1, 2, 3 and maximum n minus 1. And this basically tells about the subshells or energy sublevels that are SPDF, and I explained you in detail. This is the table. I am relating the previous table to the previous quantum number with the new quantum number. So when it is 1, principal quantum number is 1, that is K shell, then L value will be n minus 1. So n minus 1 means 1 minus 1 equals to 0. When this is 0, it has given the name S subshell. When value of L is 0, it is given the S subshell, and S word stands for short. S letter stands for short. And when n is 2, then L equals to 2 minus 1, as n minus 1. Here value of n is 2. 2 minus 1, 1. When there is 1, it means this is p subshell, and it will also contain the s subshell. And but for 1, it means this is the p subshell, and p letter stands for principal subshell. And when value of n is 3, n minus 1 means 3 minus 1 equals to 2. When it is 2, it shows the d subshell, this one, d subshell. And before d subshell, it will also contain, this shell will also contain s and p subshells as well. And d stands for diffused. D stands for diffused. This letter is from diffused. And when n, principal quantum number, is 4, then L is equals to 4 minus 1 equals to 3. 3 means d orbitals. Oh, sorry, f orbitals. 3 means f orbitals. F stands for fundamental. And this subshell will contain in this shell, in fourth shell, when there is this 3 subshell, that is f, it will contain previously the d subshell and p subshell and s subshell. So first shell will contain only one subshell, that is s subshell. So s is the orbital shell as well as subshell. While in second orbit, or you can say in the second shell, there are two shells, s, and one new one is the p subshell. When principal quantum number is 3 shell, 3 orbit, then there are 3 subshells, s, p, and the third one is the d subshell. And when n, principal quantum number is 4, when it's in the fourth orbit, you can say there are total 4 subshells, s subshell, p subshell, d subshell, and the fourth one is the f subshell. S stands for sharp, p stands for principal, d stands for diffused, and f stands for fundamental. So hopefully this will be clear for you. And we can also calculate the maximum number of electrons in subshells. Previously I calculated for you the maximum number of electrons in shells or orbits, and if you recall, in the first shell it were 2, in the second shell it were 8, in the third 18, and then in the fourth this were 32. But now I am going to calculate the number of electrons in subshells. So for S, this is calculated with the help of formula 2 into 2L plus 1. For S, I will calculate in front of you 2 into 2. When it is S, then what is the value of L? This is 0. 2 multiplied by 0 plus 1. 2 into 0, 0. 0 plus 1, 1. When this 1 will multiply by 2, we will got the answer 2. So maximum number of electron in S subshell is 2. Okay. Now I will calculate for P subshell. 2 into 2. When it is P subshell, what is the value of L? This is 1, of course. It will multiply by 1 plus 1. 2 into 1, 2 plus 1, 3. When this 3 will multiply with 2, then we got 6. So maximum number of electron in P subshell, this is 6. And you know, in this P subshell, in a shell number 2, I told you in maximum number of electron in first shell is 2, in second is 8. And how it comes 8? 6 in the P subshell and 2 in the S subshell. So total are 8 electrons. Similarly for D, calculate using this formula. So these 6 electrons are in subshell, in P subshell. In D, I will calculate in front of you 2 into 2. And when it is D, what is the value of L? Of course, its value is 2. 2 into 2 plus 1. 2 into 2, 4. 4 plus 1, 5. 5 when multiplied with 2, then it comes 10. So maximum number of electron in D subshell, it is 10. And this D subshell also it has P subshell and S subshell. When we calculate this total, 10 plus 6 plus 2, it comes 18. and we already know in the third orbit or third shell, maximum number of electrons are 18, and this comes by adding 10 with 6 electrons in p subshell and 2 electrons in the s subshell. Similarly, for F, you can calculate 2 into 2. What is the value of D for L? It is 3. Multiply 3 plus 1. 3 into 2. 6. 6 plus 7. 7 multiplied 2, then it is 14. So maximum number of electrons in F subshell are 14. So 14 plus D, it has 10. 24 and plus 6 30 and 30 and plus 2, this is total 32. So maximum number of electrons in orbit is, first orbit is 2 and it has s subshell that contains maximum 2. When second shell, it has maximum 88. How? Because it contains 2 subshell, s subshell and p subshell. S subshell has 2 electrons and p subshell has 6. 6 plus 2, it's 8. For third orbit, it is 18 and it contains these 3 subshells S, P and D. And D has total 10 plus 6 from P subshell and 2 from S subshells, total 18. And while in case of fourth shell, or to say in the fourth orbit, maximum number of electrons are 32 by adding 2 from S subshell, 6 from P subshells and 10 from D subshells and 14 from F subshells. Hopefully it is clear for you. And again I am telling you, S stands for sharp, P for principal, D diffuse and F for fundamental. And the shapes of these orbitals, and in detail we will draw how to draw the shapes in X, Y and Z axis in the next lecture. I will tell you in detail about these shapes, how to draw this shape. But for S, this is spherical, P is for dumbbell, D is for sausage, or you can say it's a double dumbbell type. And for F, it is shapes are very complicated. And students, here is the question for you, and this is very important. Which quantum number is also called subshell quantum number? Simply, if I ask you which quantum number is also a subshell, answer is in front of you, of course S. S is the subshell as well as it is the orbit, because it is itself a shell, itself a subshell. There is no other subshell in the first orbit. So S is the quantum number as well as the subshell quantum number. While the second, like it has 2 subshells, so only S is the shell or subshell. And we third have the magnetic quantum number. Magnetic quantum number represented by small m, and basically it tells about the orientation of the orbitals in the space. That I know how to calculate the orbitals, how many orbitals are in S, P, D and F subshells, and how their orientation in the space. And it explain the effect of an orbital in magnetic field, and this is related with the azimuthal quantum number as follow. How this is related to the azimuthal quantum number? Value of m depends upon the value of the azimuthal quantum number, like m is equal to plus L, 0 and minus L. You can also say m equals to plus minus L. So its value depends upon L. If L is 0, then plus minus 0. If L is 1, then plus minus 1. And that I explained you with the help of this table. And how can we calculate the values of M? Basically that is the orientation. Now I am relating this magnetic quantum number to the azimuthal quantum number as well as to the principal quantum number. So this is a I am just summarizing in front of you. When L is 0, M is, I already told you, plus minus 0, or you can say plus 0, 0, minus 0, it's all the same. So when L is 0, M is 0. 0 means only one orientation, and this is 1. And for that purpose, this is again an S. For L it is S. If it is 0, then it is S, as it is. This is 1. And when this value of L is 1, it means plus minus 1. And how to write it in openly? Plus minus 1. So in plus minus 1 there is one more number, that is 0. 1 mean plus 1, 0, then minus 1. So these are total 3 orientation. 1, 2, 3. 3. And these are for P. It means P has 3 orbitals, that are Px, Py and Pz. This Px, Py and Pz. So these 3 numbers, this shows there are 3 orbitals in P subshell. In S there is only one orbital, that is S orbital. While when L value is 1, then value of M is total 3. 1, 2, 3. And 3 stands for 3 orientation. And in case of P subshell, this is Px, Py and Pz. So total are 3 orientation. It has only one orientation. Or you can say this is the orbital. Total 3 orbitals for P and 1 orbital for S. When the L has 2, that is for D, then plus minus 2 and plus 2, then there is minus 1, plus 1, 0, minus 1, then minus 2. So these are total 5. 1, 2, 3, 4 and 5. Total these are 5. It means D subshell has total 5 orbitals and it has 5 orientations in space, like dxy, dyz, dxz, dz square, dx square minus dy square. So total are 5 orientation are 5 orbitals in D subshell. Similarly for F, when its value L is 3, for M it will be plus minus 3, and in if we expand the plus minus 3, then plus 3, plus 2, plus 1, 0, minus 1, minus 2, then minus 3. So total these are 7 orientation. 1, 2, 3, 4, 5, 6 and 7. So total are 7 orientation. It means F subshell have 7 orbitals. So S has it is subshell, it is or shell, subshell and orbital. While P has 3 orbitals, D has 5 orbitals, F has 7 orbitals. And we can calculate the number of electrons in these orbitals. Every orbital, not subshell, every orbital has maximum 2 electrons. So if S it is the 2. We have already calculated in previous quantum numbers, S has maximum 2 electrons. And in P we have calculated in P subshell, if you remember, they were total 6. How they were 6? Because every orbital contains 2 maximum electrons. So Px has 2, this one will be Px, Py and Pz. So maximum P it will be 6 by 2 plus 2 plus 2. Similarly D, there are 5 orbitals. D subshell have 5 orbitals and each orbital contains 2. 2 plus 2 plus 2 plus 2 maximum 10. We have already calculated. And for F orbitals, we have, for F subshell, we have calculated total number of electrons 14. And these 14s are divided in 7 orbitals. Each orbital contains 2. 2 plus 2 plus 2 plus 2 plus 2 and plus 2 and plus 2. This gives you maximum 14 electron in D subshell. And each orbital, remember again, each orbital has maximum 2 electrons. So in this way you can calculate the number of electrons in orbitals and number of electrons in the subshell, and you can find the orientation of these orbitals in space. And the whole discussion shows that magnetic quantum number actually determines the orientation of the electrons in the space. And the last one is, that is spin quantum number, represented by small s, This spin quantum number basically determines the direction of the spin of the electron, and this was described by Goldsmith in 1925. He suggested the spin quantum number. Okay, if electron is moving like a wave motion, and during their movement in 3 dimension, it spins, and it spins will be in the 2 direction, like it can be clockwise and it can be anti-clockwise. So it spins its own axis. If this is like south and north pole, and if it is called like its spin is, electron is spinning around its own axis, it can be clockwise. If it is clockwise, it is represented by -half or by up arrow, and if the spin is like anti-clockwise, then this is represented by +half or by down arrow. So maximum 2 spins, and previously you know an orbital contains maximum 2 electrons, maximum 2 electrons in orbital. Out of them 50% mean one will be spin on clockwise. Clockwise rotation is represented by -half or by up arrow, and remaining 50% means remaining one orbital, it will show anti-clockwise. Anti-clockwise orientation is represented by +half or by down arrow. So this self orientation rotation of the electron about its own axis, this is associated with the magnetic field and hence a magnetic moment. So, and the circular path where the electron is moving of an electron around the nucleus, that is called an orbit. I will explain to you in more detail in the next lecture what is orbit and the difference between orbit and orbital. So this was all about the quantum numbers, like principal quantum number by n, that is about shows the size, or you can say about the that tell the shells or orbits or energy levels. Azimuthal quantum, that is represented by L, and this shows about subshell. And the magnetic quantum are represented by M, that is actually shows the orientation, and like it tells about the orbitals. And the spin quantum number, that S, and this shows tells about the spin of the electron, either it's clockwise or it's anti-clockwise. So this was all about, and we will come to know that where electron is present, in which shell, in which subshell, and in which orbital with what spin. So basically these are 4 quantum numbers that represent the position of the electron in the atom. Our next topic will be shell, subshells or orbitals and their shapes. We will discuss that in detail about the shapes of the orbitals.